In this video today, I am going to talk about polysaccharides. And polysaccharides are a group of carbohydrates that consist of many repeating chains of glucose specifically. So, on this slide, this shows the major polysaccharides we're going to talk about. Today we're going to start talking about starch. I'm trying to, okay. So today we're going to, we're going to start talking about starch first, which its main role is energy storage in plants, of which we end up getting the energy from those plants when we consume them. And then we are going to talk about glycogen, which is energy storage in our bodies, in our liver and our muscle. And then we're going to talk about cellulose, which is the major polysaccharide in plants and trees and things like that. So when they are hydrolyzed, or when those units are broken down, hydrolyzed, they all will yield that right-handed glucose. The difference between the starch and the glycogen and the cellulose, and even there are two different types of starch, is how they are linked together. Those glycosidic linkages are different. So I'm going to write that word down. Again, it is one that you have seen a lot in the presentations that I've been giving on carbohydrates. So glycosidic linkages are all different for each of these types of polysaccharides. So talking first about starch. Starch is composed of two different types of substances, and one is called amylose and the other is called amylopectin. So let's look in a little bit more depth at each of those. Amylose consists of large molecules, and they are just long chains, unbranched, and they take on a helical structure. So the key point here is that they are unbranched chains of alpha glucose, and they have a helical shape. Now the good news is on the next slide I've got some pictures. Amylopectin consists of highly branched chains, and they have the 1,4 glycosidic linkages just like the amylose does, but they also have some 1,6 glycosidic linkages. Now, again, these numbers don't really matter. They're referring to the carbons. I've pointed that out before, but the point of it is that this is what makes polysaccharides different from one another, is how they are linked together. So here is a structure of amylose, and it's pointing to the alpha 1,4 linkage. Now it takes on this helical structure. There are no branches. It's just this constant repeated glucoses in a straight line, but curly at the same time. Maybe I don't want to say in a straight line. I'll say unbranched. And then they take on the helical shape. That's the best thing to say. Here is the amylopectin. You can see it's highly branched. Now there are these 1,4 linkages here, but everywhere there's a branch, we're branching off of the number 6 carbon and connecting it with the number 1 carbon. So that's where that's coming, and the branches have a slightly different linkage. And here is a representation of the amylopectin. Now, if you get some cornstarch and you're about to make gravy, cornstarch has both amylose in it and amylopectin. And depending on the source of the starch that you get, there will be different amounts of amylose and amylopectin comparatively. They'll have different ratios to each other depending on your starch source. But most starches contain each of the different types of starch. So when we consume starch, the first thing that happens is in our salivary glands, we have an enzyme called amylase. And so we have salivary amylase, and then there's also pancreatic amylase. So once this process starts, the breakdown starts in our saliva as we're chewing. It starts to break down, and we start to get some hydrolysis. And as it is making its way through our digestive tract, the starch is breaking down into some smaller carbohydrate chains, some maltose, which is the disaccharide, and then ultimately, when it gets intestinally with intestinal enzymes, it breaks down into the individual right-handed dextrose, the glucose, and from there, it can go into our blood. So we start digesting that starch immediately with the mechanics of chewing and also with the amylase in our saliva, and it just continues to break down throughout the digestive process. So hydrolysis is the primary reaction that breaks this down. Now, when we put starch in cold water, it's really not that soluble. A little bit of it will dissolve, but not really too much. If you put it in hot water, however, you can get some of it to dissolve, and this is kind of a premise for how you can make gravies with starches. One of the positive tests for starch is an iodine test, and if starch is present, the iodine will cause the starch to turn a bluish black color. So sources of starches, or what we call complex carbohydrates, come from grains, corn, rice, wheat, and potatoes. And there are a vast number of grains. There's bran and oats and barley, and I don't even know. I'm not expert on grains. I went to college to study rocks and become a geologist. Isn't it funny how life works? So I'm not a grain expert, but we're familiar with what grains are. I really like those wheat berries. Those are really tasty. You can make lots of nice, yummy dishes with wheat berries. All right, the next one that I want to talk about is glycogen. Now, if you are taking a walk outside and you decide you want to burst into a run, your body's going to demand more energy. And as you are exercising or even going throughout your day, if you use up all of the glucose that's in your blood for energy, your body, your sugar, your energy level, or your glucose level gets lower in your blood. And your body has a mechanism to go to its glycogen stores. Sorry, I have to fix my pants. They're bothering me. So, glycogen is stored in your muscles and in your liver. And it is highly branched, just like amylopectin, but even more so. This is just a comparison. When you look at amylose, remember it does form helices. The branched amylopectin and extremely branched glycogen. Very similar structure to amylopectin, except there are many, many more of those alpha-1,6 branch linkages occurring more frequently. So again, glycogen is where we store energy in our body. And when we have other ways to store energy in our body. I mean, fat is a way that we can store energy in our body. And when we talk about metabolism and what takes place when we consume carbohydrates versus proteins versus fats, we will continue on with these conversations. So I really like this picture. I think it's really artsy. This is a glycogen. glycogen structure. And you can see it's highly, highly branched. And in the center, there is a glycogen, which is an enzyme that it catalyzes the formation of glycogen. So what would trigger our bodies to start storing the glucose? And this is what happens. So here is some glucose. There's glycogen in the muscles and also in the liver. When our blood glucose levels get too high, insulin is secreted from the pancreas. Now this triggers this reaction right here. It triggers this glycogen enzyme to start pulling that glucose from the blood and linking it together to form glycogen, of which is stored in the liver and in the muscles. So also the insulin not only triggers the uptake or the formation of glycogen, it also triggers the uptake of glucose into the cells. So it's this cascading effect, like your cells start taking the glucose into like across the cell membrane through these channels, and all of a sudden your blood levels are back where they should be because our body just does these miraculous things. Now, when our blood glucose levels get low, or when we are in demand for that energy, the pancreas releases glucagon, and this triggers the breakdown of our glycogen. So we go to our glycogen stores now, like, oh, my blood doesn't have enough glucose in it, so oh, here comes the glucagon, it's going to tell my body what to do, and this is what it does. It starts breaking these chains, and right off the end, the glucose comes off and goes into your body wherever it's needed. So it's really miraculous. When we talk a little bit more in detail about diabetes, we will learn some of the mechanisms that can get in the way of this our body's natural way to control blood sugar. This just kind of summarizes the same thing. So here we have high blood levels of glucose. The pancreas secretes the insulin, which triggers the glucose to be taken up into cells and taken out of the blood. Okay, so here is the opposite. If we have low, our blood glucose level drops, the pancreas releases glucagon, and then we get the liver and our muscles releasing the glucose from that stored glycogen into the body where it's needed. So a really, really neat process. So the last polysaccharide I want to talk about is cellulose. And cellulose is wood fiber, essentially, and plant fiber. What's really cool about it, it is the most abundant. Nobody puts baby in the corner. Do you get the reference? It's Dirty Dancing. And I was referring to the fact that I was down in the corner down there, although I'm putting myself up in this corner here. So isn't that weird? Cellulose is the most abundant organic substance on the planet, and it is the chief structural component of plants and wood. We do not possess the enzyme to hydrolyze the cellulose, and therefore we can't digest it. And in our diet, with our dietary intake, we refer to this as fiber. Fiber is an important component in our diets. It helps keep our digestive tract healthy. However, we cannot take these chains of glucose and hydrolyze them to get energy from them. Cows can, and horses can, and so can goats and other ruminants. But We can't. If we consume plants and there is cellulose in it, it essentially passes through our body unchanged, but it does add bulk to the materials passing through our digestive tract. So the chains of glucose are joined by beta 1,4 linkages. Starch linkages were alpha linkages. And the way that these linkages work, it allows for extensive hydrogen bonding in the cellulose. Now, cellulose, I'm just going to jump ahead a little bit. So cellulose doesn't form these helices like starch does. It forms, because of the nature of the beta 1,4 linkages, it has more of a straight structure. And what happens is there are extensive hydrogen bonds occurring between these straight structures. And these are plant fibers. This is what makes plants so fibrous, which is why I wanted to include this image here of the plant, and these are the plant fibers. Now, if you split the wood with an axe or a hatchet, or your elbow or your foot or your karate chop hand, this is what's happening. So we have these chains of cellulose like this, and between those chains there is extensive hydrogen bonding, and what we're doing is we're ripping through those hydrogen bonds. And since the cellulose forms these long chains of glucose and our hydrogen bonds are connecting another long chain here, we're splitting down the length of those fibers and just cleaving right through those hydrogen bonds and separating cellulose from one another. So here in this image, I have marks all over the place. I use my handy dandy eraser. That's fun. This shows a two-dimensional representation of that cellulose, and then this 3D shows all of the bonding, and the hydrogen bonds are always, as they have been throughout the course of the biochemistry course you're in, represented by this dot, 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 dot. So cellulose, again, is what makes up the insoluble fibers in our diet, fiber, and that's an important component to adding bulk to the waste and help eliminate it more easily. Most of us don't get the amount of fiber that we should be getting each day. It's recommended that we should get between 20 and 45 grams per day, and most Americans get only about half of that. I have an apple here because it's a really good source of fiber. And a place you can get fiber is through eating whole grains and fruits and vegetables, in particular the peels. And it is essential for colon health. There are lots of fiber supplements out there, the psyllium fibers. I can't think of any off the top of my head right now, but there are lots of supplements out there that can increase your colon health if you are not getting enough intake from your diet. So this final slide just kind of summarizes the difference between the polysaccharides. And again, cellulose is very straight. It has beta glucose in it. All of the other polysaccharides have alpha glucose. And linkages involve connections between the number 1 carbon on one glucose and the number 4 on the other. Because these are beta 1,4 linkages, it has a much different structure than alpha 1,4 linkages. And as soon as we get in these 1,6s, we get these highly branched structures. And the crazy part about this is it's all glucose. These are all chains of glucose, and they all serve different purposes, and it's really quite amazing. I hope that you learned something about polysaccharides in this presentation, and I wish you well. Thanks for watching.